Hi guys, welcome to Learning Electronics Repair, and this video needs a little bit of an introduction. So, as quite a few of you know, I like to build homemade test equipment, and especially homemade test equipment that you can't generally buy. So in this video, sponsored by PCBWay.com, I'm going to look at some of the test equipment that I've actually built. These are projects which I put on PCBWay, so you guys can actually order these and build them yourself. Okay, and we're going to use a couple of these products in a real life repair scenario. So this is an actual repair, and you'll see how useful this equipment was. In fact, I think you may say I couldn't have actually completed this repair without this equipment. Okay, let's have a look at the repair we're going to undertake. Let's have a look at the equipment we're going to use, and then let's get on with the job. I have an amplifier here, well, part of it. We looked at this, I checked back actually, it was 7 or 8 months ago. Okay. Citronic Pro 1000. And this had one blown channel. So this channel was working, the other one wasn't. We can see the power supply board here. There's another input or output board at the back. Yeah, this is where the speakers attach and some switches and things, okay. Oh, and the inputs, alright, so that there. The fault which I diagnosed on this amplifier module, which I'll show you in a minute, is a P-channel MOSFET, P-type. And this is a Class G amplifier. And you can tell that pretty easily, I think. And probably if you've watched quite a few of my videos. So when you get lots of capacitors like this, and there's 4 pairs, okay, you'll often find that these are Class G amplifiers, which have 2 different voltage rails, a high voltage and a low voltage. Yeah. Again, another clue for that is 2 bridge rectifiers, one for each voltage rail. So that's what we have. And with the Class G amplifier, you have MOSFETs which switch the supply to the output transistors from low voltage, well, say low, about 50 volts maybe, and high voltage about 100 volts, okay? And one of those MOSFETs on here was short circuit, and that's the actual fault. I bought some replacement MOSFETs. This was some time ago now, around the time I was building the fake MOSFET detector, and I seem to recall that the MOSFETs were fake, the ones that I bought. The reason it's been here so long, you might ask me, why has this been here 7 or 8 months? Well, this is from a guy who brings me a lot of repair work in. This belongs to one of his customers, and he said to me, oh, don't bother about that, he doesn't need it back till Christmas. So it's been sitting on one side, but he messaged me last week and said, oh, probably a good time to look at that amplifier now, because, you know, Christmas is, well, coming along, yeah. Some way away yet, but coming along. So let's get back to this. I checked and I can see that I have bought another lot of MOSFETs. So after I found the fake ones, I ordered some more from a different seller on AliExpress again, okay. So what I have is, I have some of the original MOSFETs, at least the short circuit one, but I do have good working original ones on the amplifiers. I have the first batch I bought, I have the second batch I bought. So I think the first thing is we need to have a look at these MOSFETs, look at the data sheet, and see if the second batch I bought are more original, or at least seem to be within spec. I mean, I actually don't care so much as long as they're within spec, yeah, RDS on and VGS threshold. So let's have a look. Here is the amplifier channel which had the fault on it. So we have 2 PCBs plus this one at the back, okay. Heat sinks have been taken off. This is just the little covers, yeah. So here is the board. I was looking on my old video, this looks really blackened here actually. Yeah, but I actually think this is just like some sort of coating on here, conformal coating. Let's just give that a bit of a clean anyway. These are transistors, PNP. And these are MOSFETs, okay. So you can see IFPFZHDO, although what's fitted appears to be something different from that. IR, well, it says P639K by the looks of it. Something like that. Other one, 1620 RG. That says MUR 1620, okay? This is the one with the bad MOSFET, and this one says IRF 4905 and MUR 1620, which is the same as that one, okay? These two boards are different, so you can see this has the 2SC 5200s, 2SA 1943, so these are PNP power transistors. These are NPN. Okay, you can just see, yeah, 2SC. So these two boards are effectively the complement to each other. Yeah, the two halves of the amplifier, if you like, the positive and negative side of it, and that's why these MOSFETs are different. So without dismantling the other one, which I don't really want to do, I don't have a good original MOSFET IRF 4905. What I do have is the one I removed. Yeah. Leg cut off, it uses a tab for that connection. Okay. I have one here. And one here. Okay, and these are different. So this is the second bag of the ones I actually bought. And these are this type of logo. Okay, actually could be the first bag, I'm not sure which were which now. But they have that type of logo. I have a few more of them in the bag. Okay, we can see these were sold. IRF 4905. Yeah, P channel, 74 amp, 55 volt. Okay, new original. Yeah. And the other ones I bought are these. So IRF 4905 again, power MOSFET. And these ones are like that. Okay, so that's one of those ones. So we have different markings from one batch I bought, the other batch I bought, and the original, all different. In fact, I seem to have even more types than that. So these 6 are all marked the same. Okay. These ones were saying 9013, that says ST60, that says ST60. So those 5 are all the same. That one is marked a little bit different again. I think you can see the actual difference in the IR logo. Okay. These have a completely different IR logo. Again. So those 3 are different. Those 2, or rather at least that one is different. Okay, and then that's the original one. Right, let's look at the data sheet. And this tells us minus 55 volts. I always like this minus 74 amps, like you can actually have a negative number of amps, yeah. But anyway, RDS on 0.02, which is the maximum in fact, okay. Measured voltage gate source, 10 volts. And drain current at 38 amps. Now, I can't measure these at 38 amps. I can't measure them any more than 10 amps with the power supply I have. I'm going to get a 30 amp power supply actually, I think, but I don't have one at the moment. And in any case, if I do that, I'll have to modify the test a little bit, lower value resistors, or more of them, more likely. So I can only really test these at 10 volt and 10 amp. But I'm interested to see if we can see any differences, and especially if any of them are well out of spec. And here we are on PCBWay.com. We can now have, for example, 60-layer PCBs. Wow! Flexible PCBs, aluminium PCBs, and there's even design contests. So you can actually win yourself some money on here if you're so inclined. But let me show you the shared project which we're going to be using today in a real life repair situation. Here are the various projects I've uploaded, and we've built all these things on the channel, to be quite honest. Some of them were very, very useful. The Mr. Bleep, the multi-load definitely. Uncle Sweepy, that was an interesting one. Audio sweep generator. The ominous op amp tester, this one has proved very popular and I use this in my repairs. You will see that. And of course the fake MOSFET detector tester. Okay. So with these shared projects, you upload your design. You can get some PCBs produced first so you can actually test the design to make sure it's okay. And then you can move it to a shared project. You have the option of making them PCB only, which is this one, or the project can also be pre-built. So you can actually upload the bill of materials and the Centroid, which is basically the pick and place file. These are generated from your PCB design software automatically. And then people can actually order pre-built PCBs as well. This one being a through-hole project is PCB only. Okay, a link there to my video, you can see that. So I'll actually put that in the video description here, and I'll also give you the link to all of my projects, this one. Okay, so that's what we're going to be using today. But first of all, let's try the analyzer. So this is the one which I thought was short, as I remember. I'm sure this one was short. Yeah, short, red, blue. Okay, so drain source. Now this is testing these at very, very low current and voltage. This is the one that's different from all the others. What's it tell us? Well, it says it's good. It tells us the gate source voltage is 1.05 threshold. And the spec is telling us a minimum of 2 and a maximum of 4. So that is actually well out of spec, but bear in mind this is at very, very low current. So I don't think this will give you an accurate reading of that. And this won't tell you the ODS on. Now we have this batch which are all the same as each other. Well, that's completely different. I mean, really different, and that's still within spec though. Okay. We'll just try a couple of these out of this batch. See if they're very similar to each other. Yeah, very close. So those 6, at least the gate source threshold voltage within spec, that one is well out of spec. These 3 are all the same as each other. P channel. That's around the middle of the spec, okay. 2.95 again, we'll just try another one of those 3. See if they're similar to each other. Yeah, same as each other. And then the last batch, which are all the same as each other, but different from the others. 1.89. So, again, that's below the spec, but bear in mind, I can't really get a proper reading because of the current. We'll try this again on the actual fake MOSFET detector, okay? What does this one give me? Just another one of the same. Yeah, 1.89. So we can certainly say that the 3 or rather 4 batches are different from each other. That is for sure. Okay, let's get the fake MOSFET detector. And I have one already bolted to it, which I think was the same as these ones. Let's have a quick look. Yeah, that's one out of this batch, okay? Okay, so 10 amp bench supply. I've set it to 10 amps maximum. The meter is connected directly across the MOSFET drain source, okay. I'm going to turn up the voltage on the gate, okay, and you'll see this is the voltage across the MOSFET, okay, which is basically the supply voltage until the MOSFET starts to conduct. Now, we can turn this up until, with a bit of luck, if I get the camera right, you'll see the LED come on. There, okay. So just as the LED illuminates, this is saying 4.8. Okay. Now, if you watch, you'll probably see that the voltage on here starts to drop before the LED comes on. That's because I need enough voltage drop across the load to light the LED. At which point the MOSFET is already conducting. So if we watch this, there's another possibility, and we increase the voltage slowly. This will keep it increasing, and at some point this will start to decrease. When this starts to decrease, at that point the MOSFET switches on. Okay, keep going. There, you see it's gone down a little bit. I'll come up and there it goes down. It's about 3.84. Okay. So if we divide 3.84 by 2, we'll call it 3.8 by 2. Okay. That gives 1.9. And on the peak meter, this thing, these read out 1.86. So that is switching on at a lower threshold voltage than you would expect, okay? The other thing we can do is to measure the RDS on, the resistance when the MOSFET is on. So what we do is with this, we just turn this up until it limits at 10 amps. And we measure the voltage again across the MOSFET and see what we see on this meter, okay? So it's limiting and it's saying 0.087. I won't let it run for long. It is water cooled, this thing, okay? But let's just go again. So 0.087, then it starts to climb up a little bit. So that is the voltage drop across the MOSFET, and from that we can work out the RDS on. And to do that, we need to make a note of the current. So the current, 10.1 amps, okay. So to measure the RDS on, resistance, we use Ohm's law, R equals V over I. Okay, the voltage across the MOSFET was 0.087. Current, well, let's call it 10. It was 10.1, but it's close enough for this. So, easy maths, that comes to 0.0087, which we can round up if you like. 0.009, okay? And the data sheet, well, that tells us a maximum of 0.02. So it's roughly half of that. Bear in mind, we're only testing at 10 amps. We're not duplicating the test conditions in the datasheet, okay? But that seems pretty good for me. The only thing I will say is the gate threshold voltage is a little bit below the spec. Now let's try the one that was different from all the rest, okay? The singleton. So this one, according to the peak, had a gate threshold of 1.05, which is really out of spec. Let's see what this tells us the gate threshold is. So again, we can turn it up until the LED lights or when this starts to drop. Okay, so well, LED lights now, and this is dropping. Okay, let's just go below that, so it's sort of switched off again. Let's come back up. 1.3, 1.68, 1.7, 1.8, 1.9, 2.2, 2.3. Okay, then it drops. So half of 2.3, about 1.15, which is roughly again what the peak analyzer said. So that is well out of specification. Okay, so here is the third batch. These ones, well, to remind us, Yeah, 3.89. So that is definitely in spec, whereas the first ones were a little bit just below the minimum. But does this pass the ODS on test? Okay. Let's see. So once again, watch the meter or watch the LED. Well, there's the LED there. Let's just go down a bit. So yeah, it increases as I'm turning this up. 7.6, 7.8, 8, 806, and then it drops at 806. So that's giving threshold voltage of 4, which is the maximum within spec. Okay. Yes, it was a fraction over, but the actual datasheet only specifies to 1 decimal place, so you can't really, you know, take account of all those ones down there. Yeah, that was 4. Right, how about the ODS on? Let's have a look. So, here we go. Oh. That's bad. That's really bad. Yeah, it's 2 point something. Just let it cool down a little bit. It's in the water anyway. We go again. So 10.1 amps. 3. It went 2.9. They'll go up as it warms up. That's warming rapidly. That is way out of spec. So 2.9 divided by the 10 for the rough maths is 0.29, and the maximum allowed is 0.02. That's more than 10 times out of spec. They are absolutely no good. Okay, so just to remind ourselves, this is the last batch. Okay. .95. So that's pretty much bang in the middle of the spec. 2 to 4. Okay. So we'll measure that on this again, see how close it is. So well, that's where the LED lights. So it's 5.9, 5.8. Okay, so it's about 5.9. It goes down. So half of 5.9, yeah, 2.95. So we can say that the actual peak analyzer does a pretty good job of measuring that actually. But what it can't do is this test, and this is the important one. We're finding that already. Okay, so ODS on 0.22. Again, 10 amps, 0.22. So the results. Well, this one, IRF4905, IR logo, measured voltage gate source on or gate source threshold 1.9 volts, which is slightly below spec. Okay, but you could say it rounds up to 2, and the datasheet was only to 1 decimal place, so yeah, maybe. ODS on was actually below, but the rating we have at 0.02 is a maximum. It could be less than that, so this one is well below that, about half of it. Judging from the test we could make, that seems reasonable. Yeah, maybe. This one, so gate source on, gate source threshold, and just look at it. That is the logo. Have a good look at what this looks like. Okay, that one, this is well below specification, well below, and the ODS on is 5 times the maximum. Okay, now you might think 0.1 of an ohm isn't a lot, but if it's supposed to be 0.02 and it's 0.1, that means for every volt dropped across the MOSFET, you get 5 times the wattage dissipation. Yeah, just bear that in mind for a minute. 5 times the watts. Yeah, that's why this is so crucial. This one, well, right at the top of the limit for the spec, and they're all 4905, yeah, clearly marked 4905. And this one, again, clearly marked 4905. Look at the logo, you can see it's different again. That is bang on the top of the limit, but it's on the limit, it's not above it. This is something like 15 times more than it should be. That will just self-destruct. Yeah, that'll be it. This one, you can see the logo, a much fatter looking IR logo. Okay. IRF4905. That is right in the mid-range. And you might think 0.022 is above spec, but again, it only specifies to 2 decimal places on the data sheet. So that would be 0.02. Okay. I suspect this is the most likely to be a good one. Although this one measures as a better MOSFET on that test, okay? Can we pin this down further? Yeah, in 2 ways we can. So the data sheet tells us voltage drain source minus 55 volts, okay? So that's with the source positive to the drain. We can test this like so. Turn the voltage down, turn the current down. I have the positive to the source, the negative to the drain, and then I have the source connected to the gate. So that's to stop the gate floating. So we should be able to increase the voltage here above 55. Okay, if it goes above 55, it's fine. It passes the test. And this one doesn't. Look, 35.9. So that can't withstand the voltage. So that is a fake. We've only got one now that actually is possibly any good. So let's look at it. Okay. Well, that went to 73. Yeah. So that one is going above 55. So that is a good one. And that's that one. Yeah, the one I thought was most likely to be a good one, even though this measured lower. But that can't withstand the voltage. Yeah. So, as I said at the start, this is a PCBWay shared project. I will link it in the video description. You can order these PCBs now. Okay, I'll also link one of the videos where I actually built this so you can see it. That, I think, is an invaluable piece of equipment. I'll be very interested to know how many of you guys have got these. Have you built them yourself? Have you ordered them? Are you thinking about ordering one now if you don't have? Because you know what? Without that, I would be blowing all sorts of things up. Okay. This helped to sort the men from the boys, clearly. That one. Which brings us down to the only one which is good. And another possible test you can do is this one. So, some of you guys have seen this. This is my prototype transistor destroyer, if you like. So what this actually does, it destroys fake transistors. It won't destroy genuine ones as long as you stay within the specified ratings. Okay, this allows you to increase the current passed through the transistor 1 amp at a time. And if it goes short or open before you reach the rated value, it's fake. So this was the prototype. I have 2 versions of this. Again, I'll link the videos. Both of those PCBs are now ordered from PCBWay. So we will build them. And not only am I going to build them, but I'm also going to modify this to get even more current. I've seen some transistors that want 20 amps plus. So one thing I have on the way is a higher rated power supply. Yeah. But in actual fact, because this is current controlled by the resistor, you could just use, you know, something like an ATX supply maybe, something like that, yeah, which give you 20 or 30 amps off the 12 volts, okay? You could experiment with that. But to have another bench power supply coming along, 30 amp one, we'll modify this and we'll be able to get even more load. And that, again, would tell you if these are good. I mean, this one has passed all the tests so far. That sort of test would allow us to stick 30 amps through it. Having said that, the data sheet says 74, so it's still above what we can do, but it's another possible test. So once I have the PCBs, and they should be here this month from PCBWay, let's get those built as well. And then what we can do for certain, the 3 that fail the tests, let's see what they do if we stick a lot of amps through them. Yeah. Okay, hope you enjoyed that. Thanks to PCBWay.com for sponsoring this video. Thank you for watching. Even more thanks if you'll comment down there. Let me know what you think. Yeah, and I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.